Okay, let's continue our variation relationship exploration. In the last video, we looked at direct variation. In this one, we'll look at the remaining two relationships, starting with inverse variation. Um, and we'll go through the same process of deriving proportions and talking about the meaning of these in turn. Just move this tab out of the way. Inverse variation is symbolically represented by xy equals k, so a little bit different from our direct variation. Our direct variation was y equals kx. Here we have xy equals k, where the product of an x and y is the constant of variation. So, well, let me wait a minute before I say too much about this. Y varies inversely as x, as dictated or controlled by the constant of variation k. What does this mean in plain English? Well, here's an example. If we're examining the inverse variation relationship of xy equals 12, what's really happening mathematically? Well, as the values of x change or vary, so will your y values. And the nature of this change is dictated by the constant of variation of 3 in this case. Except it's not 3. That's a typo. That's the same constant of variation from the previous problem. In this case, the constant of variation is 12, right? Because the product of x and y is 12 now. Now, so far I have not really made a huge distinction between this kind of variation and the direct variation we had. So here's a generality. Generally, when you're looking at direct variation relationships, again, y equals kx, as x increases, so does y. And generally, as x gets smaller or decreases, so will y. Not true here. Here, because the variation is inverse, right? We've got xy equals k. If x increases, that forces y to decrease, to balance out and give us a product that doesn't change. Similarly, if x is decreasing, y is going to have to increase. So it is likely that the word inverse variation refers to this, how one variable is decreasing or moving in one direction while the other variable has to change in the other direction in order for the product to be the same. So that's one difference between the two relationships. Of course, the equations are different as well. Again, we're contrasting y equals kx for direct variation to xy equals k for inverse variation. Let's kind of work this out a bit with some numbers. If I could just scroll down here. So with this particular relationship of xy equals 12, if x is 2, for instance, then y is going to have to be 6 because the product of 2 and 6 is 12. Now notice that when I change the value of x, I increase it to 3, then y is forced to decrease down to 4 so that my product is going to be 12. And I just discovered another typo. That should be 3 comma 4 so that the product of 3 and 4 is 12. So apparently the more I explain and have to kind of communicate the concepts, the more I pick up on my own errors. So I hope you're enjoying seeing those. Now moving forward, of course, we want to see what the connection is to rational expressions. There is going to be a proportion here for inverse variation relationships, so let's generalize again using pretty much the same process we used earlier. So the general inverse variation relationship is that xy is equal to k. And if I look at a specific situation for some x and some specific y that are associated with each other, we expect to get k. Change in my pen color. And for some other x, x sub 2, and some other y that's associated with it, I should also get k, that constant of proportionality. And here they're both solved for k, so let me just choose a third color. That means that x sub 1, y sub 1, their product should be equal to x sub 2, y sub 2. Now doesn't look like a proportion, although technically it is because each of these can be written over 1. So if you wanted to, you could just do this and say I'm done. But most people choose to do a little bit of rearranging. So let me just write it again. X sub 1, y sub 1 is equal to x sub 2, y sub 2. People like to have a kind of a traditional aesthetic to this or form to it. So for instance, and this is not the only thing we can do, we could decide to divide by y sub 1, in which case they cancel out on this side, leaving me with x sub 1 equals x sub 2, y sub 2 over y sub 1. And then I could decide to say, well, let me move the y sub 2 over. Let me multiply this entire thing by 1 over y sub 2. So these would cancel out here, And what am I left with? X sub 1 over that y sub 2 is equal to x sub 2 over y sub 1. This is the proportion for inverse variation relationships. And again, if you were to flip this ratio over, you would flip this ratio over, it would be just as true. So we're now kind of armed with both an equation for inverse variation and a proportion for inverse variation. How do we do some problem solving of purely numerical problems? So we're armed with both of these tools. Let me zoom out a bit to open up a little bit more writing space here, but you're going to have some flexibility in terms of how you solve these problems. Again, let's kind of dissect this a little bit. Very first phrase, if y now varies inversely. So we're not looking at direct variation anymore. We're looking at inverse variation. So you almost want to partition this part of the question off, okay? Now I know I'm dealing with this relationship here, or this proportion here. As x and y equal 14, whoops, and I just, even in reading it, I spotted a mistake in the way I read it. I really should cut this off a little bit further down the line. If y varies as x, and you cut it off. Okay, now this teaches me that the variation relationship is inverse. And now here come the facts. Y is equal to negative 14 when x is equal to 12. So I can interpret that as for some y, I have negative 14, and for some x, I have 12. And I'm trying to find some other x sub 2, when, just crossing that out, when y sub 2 is equal to 21. And I can solve this two different ways. Let's solve it using path 1, which is you're going to find the constant of proportionality and use that to solve. So what do we have here? X1 is 12, x sub 1 is 12, y sub 1 is negative 14. And if I multiply those two, that should give me the constant of proportionality. And I think that's negative 168. Now that's not the answer I'm looking for, that's just the constant of proportionality. So now I know that for any x and y, when I multiply them, I should get negative 168. And in this particular example, I'm looking for x sub 2. I'm looking for a second x value. And my y sub 2 value is 21. And their product is going to be negative 168. So I'm going to divide by 21, in which case x sub 2 is equal to negative 8. So that's what happens with path 1. It's unavoidable. You have to find the constant of variation, and in doing so, you then get this equation here, which allows you to find any xy pairings. But you might choose not to do this at all. You might say, nope, that's too much work. I want to kind of get to the answer in a much more direct way, and that's certainly an option. We can grab this proportion of x sub 1 over y sub 2 is equal to x sub 2 over y sub 1. Incidentally, I can't commit this to memory. I never do. This is what I walk around in my daily life and use, because from this equation comes this proportion. But if you happen to have this on hand, then you've labeled them. Let's label them again. This was y sub 1. This was x sub 1. These two go together. This is some second x value, and this is some second y value. So x sub 1 is now 12 over y sub 2, which is 21, and that's going to give me this missing x value here compared to negative 14, I think. So now we can make use of cross products. You get 21 x sub 2 is equal to 12 times negative 14. The rest is just algebra. And so x sub 2 once more is going to be equal to negative 8. You've just solved an inverse variation problem. Now, none of these has any real meaning. This is just pure math. And as I promised you, when we come back to class together, we'll actually be solving real-world situations that vary directly, inversely, and jointly, which is the third kind of relationship. But for now, we're just learning how to use these concepts and these tools. So let's go to that third relationship now. And that third relationship is known as a joint variation relationship. It's symbolically represented by y is equal to kxz. Every single time we look at these variation relationships, that k shows up, that constant of variation. You always have an x and a y. This time we're adding in another variable. And what's happening? Well, your output of y is dependent on whatever you choose for x and z, and again, the puppet master is k. So I'm not going to read this out. But here's a specific example of y is equal to 4xz. I've chosen to make the constant of variation 4. And let's look to see what happens here. When it comes to proportions, I decided to kind of save you the labor of seeing me go through the derivation because you saw me do it for direct and inverse variations. So here is the proportion, or a proportion, that you can use for joint variation. And I won't read it out because it's right there in front of you, but we will use it together. So when it comes to joint variation relationships, you are now in possession of two tools, both the equation and the proportion. Again, I'm confessing to you, I cannot commit these kinds of proportions to memory. My brain just does not work that way. But I can easily become familiar with this equation, which it's very difficult to forget, and it serves you just fine. So rather than solve this problem twice, let's just solve it using one of these methods. And the method that I'm going to reveal my bias. The method that I prefer is using the equation. And let me look carefully. If y varies jointly as x and z, cut it off right there. Cut that off. You now recognize that you're not looking at a direct variation or an inverse variation relationship. You're looking at a joint variation relationship. It is telling you that y changes according to the values of x and z. And the implication is that it changes with respect to some constant of variation. That's understood. Okay, so I'm going to do some selective erasing here. Highlighting and all that business is cool, but excessive marking on the paper is actually pretty distracting. So I'll cut this off here. It looks like y sub 1 is 60 when x sub 1 is 3 and z sub 1 is 4. Think of it as, this y, x, and z all belong together. They make a particular equation here true. Now, for some other y sub 2 and x sub 2 and z sub 2, we'll also have a true relationship. And what we're trying to find is the value of that y sub 2. So y is equal to kxz. I know that for the first example, y is 60. I don't know what k is, but I'm about to find it. X is 3 and z is 4. I find that 60 is equal to 12k, which means that that constant of variation is 5. So for this particular situation, y is equal to 5xz. And now I've got the green light conceptually to go figure out what's happening here. I need to find another y value when x is 6 and z is 8. And this has turned into just a multiplication problem. 30 times 8, we're looking at 240. Excuse me, please. We have just solved a direct variation, joint variation problem. So I did also want you to kind of get some graphical connections here. Let me see if I can toggle the screen for all three relationships. So in Desmos, I prepared for you, here's the direct variation relationship. I don't mind labeling that. This is the direct variation relationship. And as I promised you, it's pretty much just a linear function, except that the y-intercept is always going to be 0. It's understood to be 0. So direct variation relationships always, 100% of the time, pass through the origin. And the only value that I can really alter here is k, right? So as I change that constant of variation, the graph becomes steeper or less steep. Okay, no big insights here, frankly. Operates essentially like a linear function, but again, always passes through the origin, which is what actually makes it proportional. This is what causes it to have this proportionality, the fact that it passes through the origin. If we now look at another relationship, the inverse variation relationship, here it is, and that, I'm kind of smiling because this inverse variation relationship looks just like the parent function, or looks a lot like the parent function for f of x equals 1 over x. And you're seeing, again, another connection between what we're studying and how it connects to these variation relationships. As in this case, I've got k set to, let me change it back to 1. There we go. So as the value of x changes, let's say x gets bigger, then y would have to get smaller. As y gets smaller, x has to get bigger. And as you change this constant of variation, it causes a transformation to the function as well. So for instance, I don't know, let's go to 6. Now you need two values, an x and a y, whose product is equal to 6. So no matter where I click, I'm trying to find a place where there's just integers, so it really makes sense. Clearly, 2 times 3 is 6, but no matter what value I go to, and I'm going to go to 3, and 3 times 2 is 6, you can see that this relationship is always holding true no matter where I am. And if I choose some random decimal value, I assure you the product of 3.28 and 1.829 is also 6. So the graph for, man, there's so much erasing to do here. The graph for direct variation relationships was effectively a straight line through the origin. The graph for inverse variation relationships was effectively the rational function, where it's broken up by that vertical asymptote into two pieces. And you might wonder, well, what does the joint variation relationship look like? Just like the direct variation relationship, except now I've got another value that I can control. Not only can I control it with k, the rate at which things are changing, I can also change it with z. Because remember, y is now codependent. It depends not only on the value of x, but also on the value of z with respect to whatever k is. So if k is 4 and z is 2, for instance, right? The k value and the z value are locked in. We've got a product of 8. So what we can now control is the x value. As we plug in some x value, that will then impact y. As x gets bigger, y will also get bigger. You can see that graphically. X is getting bigger in this direction, while y is getting bigger in this direction. As x gets smaller, y gets smaller. So I hope this has been helpful. I certainly had fun putting it together. Thank you for watching.